The universe does not shout in human language, yet occasionally it sends an unmistakable signal that something extraordinary has entered the stage. The arrival of 3i is one such signal, a messenger from beyond the gravitational authority of the Sun. This is not merely a comet or asteroid following a predictable elliptical path. Its orbit is hyperbolic, its velocity excessive, its origin unmistakably interstellar. Mathematics reveals what intuition suspects: this object does not belong here. For billions of years before its detection, 3i wandered through the vast darkness between stars. Interstellar space is not empty in the poetic sense. It is a near perfect vacuum where temperatures approach absolute zero, where atoms are sparse, and where time stretches endlessly. In that immense silence, 3i traveled alone, untethered, sculpted by cosmic rays and micrometeoroid impacts, its surface altered by radiation from distant stars. When it crossed into the gravitational sphere of the Sun, it entered a new dynamical regime. Solar gravity bent its trajectory, accelerating it toward perihelion. Telescopes captured its faint light, and orbital mechanics confirmed the extraordinary eccentricity greater than 1, velocity exceeding solar escape speed, direction inconsistent with solar system formation. This is an immigrant from another stellar nursery. Like ʻOumuamua and Borisov before it, 3i expands the narrative of cosmic exchange. These objects prove that planetary systems are not isolated fortresses. They are dynamic systems that eject debris into the galaxy, sharing fragments across light years. 3i represents a fragment of alien geology. It formed in a protoplanetary disk around a distant star, within a cloud of gas and dust collapsing under gravity. Their temperature gradients dictated composition. Ice is beyond the frost line, rocky materials closer to the star. Gravitational perturbations from massive planets may have flung it outward, ejecting it into interstellar exile. Now, illuminated by the Sun, it reveals itself not as a random rock but as a scientific treasure. Every photon reflected from its surface carries encoded information about chemical bonds, mineralogy, and history. Its brief passage transforms abstraction into measurable reality. The cosmic ocean is vast, and 3i is a drifting bottle containing a message written in chemistry and motion. Its arrival marks a turning point, proof that interstellar visitors are not anomalies, but inevitable consequences of galactic evolution. The discovery of 3i is a triumph of human ingenuity. The asteroid terrestrial impact last alert system scans the sky relentlessly, designed to detect near-Earth objects that might pose danger. Yet its true power lies in constant vigilance. Automated telescopes sweep the heavens, capturing wide field images night after night. Algorithms compare frames, detect movement, and calculate trajectories with astonishing speed. This is the age of data-driven astronomy. Billions of pixels become meaningful through computation. Artificial intelligence distinguishes noise from signal, cosmic rays from moving bodies. Within hours of detection, orbital elements are computed. Within days, confirmation arrives from observatories around the world. Spectrographs dissect reflected sunlight into its constituent wavelengths. Infrared detectors measure thermal emission. Photometric curves reveal rotation rates and surface heterogeneity. Each dataset narrows uncertainty, transforming mystery into knowledge. The existence of 3i demonstrates that planetary defense infrastructure doubles as an instrument of discovery. Systems built to protect Earth from impact now unveil secrets of distant stars. Technology designed for survival becomes a bridge to interstellar science. In the coming years, next-generation facilities such as the Vera C Rubin Observatory will dramatically increase detection sensitivity. Wide-field surveys will monitor billions of objects, and interstellar visitors may be identified earlier in their approach, providing extended observation windows. The fusion of optics, automation, and global collaboration transforms astronomy into a planetary endeavor. 3i is not discovered by a single telescope, but by a networked civilization peering outward collectively. This technological symphony converts faint light into profound revelation. The cosmos whispers, instruments translate. Spectroscopy is the language through which matter speaks. When sunlight strikes 3i, specific wavelengths are absorbed by molecules on its surface. Those missing spectral lines reveal composition with atomic precision. If water ice is present, absorption features near infrared wavelengths betray its existence. If carbon compounds dominate, characteristic signatures appear. Complex organics, precursors to amino acids, may produce subtle yet detectable patterns. The implications extend far beyond curiosity. Chemistry across the galaxy may follow universal principles. If 3i contains water, carbon, and volatile compounds similar to those found in 2i Borisov, then planetary systems across the Milky Way share common building blocks. This strengthens a profound hypothesis: life's ingredients are cosmically abundant. Planets form from molecular clouds rich in carbon and oxygen. Interstellar objects preserve that chemistry, frozen snapshots of formation environments billions of years old. Isotopic ratios may reveal even deeper clues. Variations in deuterium to hydrogen ratios can indicate formation temperature and stellar radiation environment. These measurements transform 3I into a geochemical archive. Each spectral measurement reduces ignorance. Each chemical signature bridges light years of separation. The study of Thyreid is not merely observation, it is comparative planetology on a galactic scale. The trajectory of Thyreid is governed by Newton's laws and refined by Einstein's corrections. Entering the solar system at high velocity, its path curves around the Sun in a hyperbolic arc. Unlike bound comets, it will never return. Its hyperbolic excess velocity reveals its interstellar origin. By tracing its inbound vector backward, astronomers approximate its direction of approach within the galaxy. Though exact stellar origin remains uncertain, statistical modeling may narrow candidate regions. As it approaches perihelion, solar heating may trigger sublimation of volatile ices, potentially forming a faint coma. Jets of gas could alter its spin state, subtly modifying trajectory. Precision astrometry accounts for these perturbations. Gravitational influences from Jupiter and other planets introduce minute changes. Precision measurements refine models daily. The mathematics of celestial mechanics transforms raw observation into predictive power. When 3ITLS departs, it will carry with it a gravitational imprint, a slight alteration in velocity due to solar encounter. Its journey continues, now subtly changed by passage through this system. The solar system becomes a waypoint in an endless galactic odyssey. Planetary systems are violent in youth. Emerging giant planets scatter smaller bodies through gravitational interactions. Many are sent inward, others are expelled entirely. Interstellar objects are the refugees of that chaos. 3IV provides empirical evidence for these models. Computer simulations predict that billions of such bodies roam the galaxy. Detection confirms theory. By analyzing its composition and structure, insights emerge about protoplanetary disk conditions around other stars. Differences in volatile content could indicate formation distance from its parent star. Mineralogy may reveal temperature history. Each interstellar visitor strengthens statistical understanding of galactic evolution. Rather than relying solely on exoplanet observations, physical samples, observed directly, provide tangible data. The Milky Way transforms into a laboratory. Interstellar objects are its specimens. The fleeting nature of 3I inspires ambition. Could a spacecraft intercept such an object? Rapid response mission concepts have emerged since the appearance of ʻOumuamua. High-thrust propulsion, solar sails, gravitational assists, these technologies may enable future interception. Pre-positioned spacecraft stationed in heliocentric orbit could be dispatched upon detection. An intercept mission would revolutionize science. Direct sampling of material formed around another star would provide isotopic precision impossible from Earth-based telescopes. Engineering challenges are formidable. Velocities are extreme, time windows are short, yet technological progress accelerates. What seems implausible today may become routine within decades. Thyreid serves as motivation, a catalyst for expanding ambition beyond planetary boundaries. The discovery of Thyreid marks not an isolated event but the dawn of a new era. Detection rates will rise as survey sensitivity increases. Interstellar objects may become annual discoveries rather than rare surprises. Statistical samples will allow classification. Rocky fragments, icy comets, perhaps even metallic remnants, each category revealing diversity of planetary architectures. Over time, patterns will emerge. Velocity distributions may trace galactic structure. Chemical variations may correlate with stellar populations. The boundary between solar system science and galactic astronomy dissolves. Interstellar objects unify disciplines. Thyreid is more than a transient visitor. It is a herald of interconnected cosmos, a reminder that the solar system floats within a dynamic galactic sea. Science advances not only by looking outward, but by recognizing that the universe occasionally sends pieces of itself directly to our doorstep. The arrival of Thyreid is not merely an astronomical event, it is a preview of humanity's long-term destiny. For centuries, astronomy has been observational, telescopes collecting photons, equations describing motion, theories extending beyond experimental reach. Interstellar objects change that paradigm. They are fragments of other star systems delivered physically into observational range. They are the first tangible bridges between solar systems. The existence of 3I confirms a profound reality: the Milky Way is dynamically interconnected. Planetary systems constantly exchange material. During the violent early stages of planetary formation, gravitational interactions with massive planets eject countless bodies into deep space. Over billions of years, those bodies drift, occasionally entering another star's gravitational sphere. The galaxy is not static, it is a slow-motion exchange of matter across unimaginable distances. The earlier detections of ʻOumuamua and Borisov demonstrated that interstellar visitors are real. 3LS reinforces that conclusion and strengthens the statistical case that billions, perhaps trillions, of such objects roam the galaxy. Detection is limited not by rarity but by sensitivity. The next generation of survey instruments will transform this field. Facilities such as the Vera C, Rubin Observatory will scan the sky with unprecedented depth and cadence. The Rubin Observatory's wide field imaging capability will monitor vast regions of space nightly, detecting faint moving objects earlier in their inbound trajectories. Early detection translates into extended observation windows, allowing deeper spectroscopic analysis and possibly mission planning. This technological leap alters strategic thinking. Instead of reacting to rare anomalies, humanity can anticipate a steady stream of interstellar visitors. With predictive modeling, orbital simulations, and global collaboration, interception becomes a logistical challenge rather than an impossibility. The concept of a rapid response interstellar probe moves from science fiction toward engineering feasibility. Space agencies have already studied mission architectures capable of chasing high-velocity objects. Pre-deployed spacecraft in heliocentric orbit could wait in readiness, equipped with high-efficiency propulsion systems. When an object like ʻOumuamua is detected, trajectory optimization algorithms could calculate intercept paths within days. Propulsion technologies under development, solar sails driven by photon pressure, nuclear thermal propulsion, advanced electric ion drives, offer velocity increments once considered unattainable. Even modest increases in achievable delta-v expand mission windows dramatically. The challenge is not fundamental physics, it is engineering commitment. An intercept mission to an object like ʻOumuamua would mark the first direct exploration of material formed around another star. Spectroscopy from Earth reveals composition indirectly. A spacecraft flyby or rendezvous would provide high-resolution imaging, in situ chemical analysis, isotopic measurements, and potentially sample return. The scientific return would rival, perhaps exceed, the Apollo missions in transformative impact. Isotopic ratios measured directly could reveal the nucleosynthetic history of the object's parent star. Variations in oxygen isotopes might indicate formation temperature gradients in its original protoplanetary disk. Organic molecules could reveal whether prebiotic chemistry is universal or regionally diverse. Each data point would extend comparative planetology beyond the solar system. The philosophical implications are equally profound. For millennia, humanity perceived the stars as unreachable lights. Interstellar objects blur that boundary. They demonstrate that matter from other star systems can be studied physically, not merely spectroscopically. The galaxy becomes less abstract, more tangible. There is also a long-term civilizational perspective. If natural processes exchange material between stars, then in principle, life-bearing debris could travel across interstellar distances. The concept of panspermia, once speculative, gains empirical plausibility. While the probability of viable biological transfer remains uncertain, the mechanism for material exchange is undeniably real. ʻOumuamua embodies that mechanism. Beyond scientific curiosity lies strategic foresight. The development of interception capability prepares humanity for broader interstellar exploration. Technologies required to chase interstellar objects overlap with those required for eventual interstellar probes. High-efficiency propulsion, autonomous navigation, deep space communication systems, and long-duration power sources are foundational for star-bound missions. Interstellar objects provide training opportunities. Each visitor allows testing of rapid mission design, trajectory optimization, and high-speed encounter science. The accumulated experience becomes invaluable when contemplating probes sent deliberately toward neighboring stars. The detection of ʻOumuamua also reshapes astronomical statistics. By measuring inbound velocities and directions, astronomers can map the velocity distribution of interstellar debris. Over time, patterns may correlate with galactic rotation and stellar population dynamics. Interstellar objects could become tracers of galactic structure. Furthermore, as detection sensitivity increases, diversity among interstellar objects may become apparent. Some may be icy comet, like bodies rich in volatiles. Others could be rocky fragments from interplanetary systems. There may even exist metallic remnants, fragments of differentiated planetary cores ejected by catastrophic collisions. Each category reveals different aspects of planetary evolution. The economic dimension cannot be ignored. Though ʻOumuamua itself may not be accessible for resource extraction, the study of interstellar materials informs models of cosmic resource distribution. Understanding the frequency and composition of such objects enhances knowledge relevant to asteroid mining and deep space industry. On a cultural level, interstellar visitors inspire imagination. They remind civilization that the solar system is not isolated. The cosmos is dynamic, and Earth participates in that dynamism. The narrative of exploration expands from planetary surfaces to stellar neighborhoods. Education systems may integrate interstellar astronomy into curricula. Students studying physics, chemistry, and engineering will see tangible examples of cross-disciplinary science in action. The excitement generated by objects like ʻOumuamua motivates future generations of researchers. In the longer arc of history, ʻOumuamua may be remembered as part of a transitional era, the period when humanity first recognized that the boundary between star systems is permeable. Just as the first exoplanet discoveries in the 1990s transformed astronomy, repeated interstellar detections transformed perspective. The Milky Way contains hundreds of billions of stars. If each system ejects even a small fraction of its primordial debris, the galaxy is saturated with wandering fragments. Interstellar space is not empty wilderness, but a sparse archipelago of drifting relics. Advanced detection reveals that archipelago. Eventually, catalogs of interstellar objects may number in the hundreds. Orbital parameters will be statistically analyzed. Chemical fingerprints will be compared. A taxonomy of interstellar bodies will emerge, paralleling classifications of asteroids and comets within the solar system. At that stage, interstellar astronomy becomes a mature discipline. Journals will publish comparative studies of objects from distinct galactic regions. Theoretical models of star formation will incorporate empirical constraints derived from these visitors. In this broader context, 3I-ATLAS represents more than a singular event. It is an early data point in an expanding dataset that will redefine planetary science. The trajectory of human exploration mirrors the trajectory of 3I-ATLAS. Just as it entered the solar system from the depths of interstellar space, humanity will eventually extend outward. Technologies developed to observe and intercept such objects lay groundwork for that expansion. The future may witness probes launched deliberately toward interstellar objects long before they approach the sun, meeting them in deep space. Autonomous spacecraft may drift for decades, awaiting encounter opportunities. Artificial intelligence will guide navigation, analyze data in real time, and transmit compressed insights across astronomical distances. Over centuries, perhaps millennia, humanity may transcend the role of passive observer and become an active participant in the galactic exchange of matter. The same gravitational mechanics that delivered 3I-ATLAS could one day assist human-made vessels traveling between stars. In that distant future, the first confirmed interstellar visitors, ʻOumuamua, 2I Borisov, and 3I-ATLAS, will be remembered as heralds. They signaled that the stars are not isolated islands, but components of a connected galactic ecosystem. 3I-ATLAS in particular symbolizes inevitability. It demonstrates that cosmic boundaries are permeable, that stellar systems share debris, that the galaxy is alive with motion. Its brief appearance within telescopic view carries implications extending far beyond its physical size. When it departs, accelerating back into interstellar darkness, it will leave behind transformed understanding. Knowledge gained from its passage will persist. Data will be archived, models refined, ambitions expanded. The story of 3I-ATLAS is not confined to orbital mechanics or spectroscopy. It is a chapter in the evolving narrative of civilization, a reminder that exploration does not end at planetary orbits. The horizon continually recedes. The future of interstellar astronomy is inevitable. Detection will improve, missions will launch, data will accumulate, and one day, the arrival of an interstellar object will no longer be rare news but routine science. Yet the significance will never fade. Each visitor will remain a messenger from distant stars, a fragment of alien worlds crossing briefly into human awareness. 3I-ATLAS stands among the first of these ambassadors, marking the threshold of a new cosmic era. The galaxy is not distant, it is interactive. And through objects like 3I-ATLAS, the interstellar future begins. 3I-ATLAS is not the conclusion of a story. It is the opening of a gateway. For most of human history, the stars were distant lights, mysterious, unreachable, poetic but abstract. Astronomy measured their brightness, decoded their spectra, mapped their motion, yet they remained remote. Interstellar objects change that relationship fundamentally. They are not distant lights, they are physical emissaries. They cross the boundary between star systems and enter measurable proximity. They collapse distance into opportunity. The appearance of 3I-ATLAS signals the maturation of a species that can recognize such a visitor. Billions of years ago, interstellar debris surely passed through the young solar system unnoticed. There were no telescopes, no detectors, no mathematics to interpret hyperbolic trajectories. Today, advanced surveys identify faint moving objects within hours. Orbital eccentricities are calculated instantly. The distinction between bound comet and interstellar voyager is determined by precision data. Civilization has reached the threshold where the galaxy's debris field becomes visible. The earlier detections of ʻOumuamua and 2I Borisov were once perceived as rare anomalies. With 3I-ATLAS, rarity begins to dissolve into pattern. Statistical reasoning suggests that the galaxy must contain vast numbers of such objects. Each planetary system ejects debris during formation. Gravitational scattering by giant planets flings smaller bodies outward at escape velocity. Multiply that process across hundreds of billions of stars, and interstellar space becomes populated with relics of planetary construction. This realization alters cosmic perspective. The Milky Way is not merely a collection of isolated solar systems, it is a gravitational ecosystem. Matter is exchanged slowly, subtly over cosmic timescales. The boundary between ours and theirs becomes porous. 3ATLS embodies that permeability. From a physical standpoint, its trajectory illustrates the elegance of celestial mechanics. Entering the solar system at extraordinary speed, its path curves in response to solar gravity. The Sun acts briefly as a gravitational lens, bending motion before releasing it. After perihelion 3ATLS accelerates outward, carrying with it the imprint of its encounter. It will never return. Its visit is transient, but its implications are permanent. Future observatories will ensure that such objects are detected earlier and studied more deeply. Wide-field surveys operating nightly will monitor the entire sky with unprecedented sensitivity. As instrumentation improves, interstellar objects may be detected farther from the Sun before intense solar heating alters their surfaces. Earlier detection increases scientific return exponentially. Longer observation windows allow higher resolution spectroscopy, rotational studies, and precise modeling of outgassing behavior. The possibility of direct interception moves from aspiration toward engineering roadmap. Rapid response spacecraft architectures are no longer speculative fantasies. Pre-positioned probes in heliocentric orbit could await target designation. Upon confirmation of an inbound object like 3ATLS, optimized trajectories could be computed using high-efficiency propulsion systems. Even a high-speed flyby would provide invaluable data, surface morphology at meter-scale resolution, direct mass spectrometry of volatile plumes, magnetic and plasma measurements during solar interaction. Such missions would represent the first deliberate encounter with material born around another star. The scientific revolution would be profound. Isotopic abundances measured directly could reveal the nucleosynthetic environment of the parent stellar system. Mineral composition could confirm or challenge models of protoplanetary disk chemistry. Organic molecules, if detected in abundance, would reinforce the idea that prebiotic chemistry is a galactic norm rather than an earthly exception. There is also a deeper philosophical dimension. Interstellar objects redefine proximity. A star may be light years away, but a fragment of its planetary system can traverse that distance and briefly share space with Earth. The cosmos becomes tactile in principle. Humanity stands at the beginning of an era where interstellar study is not purely remote sensing but direct interaction. This shift has civilizational consequences. The technologies required to chase interstellar visitors, advanced propulsion, autonomous navigation, deep space communication, are stepping stones toward interstellar exploration itself. Each intercept mission refines capability. Each engineering success builds confidence. Over time, the line between chasing visitors and launching outbound probes blurs. The trajectory of human exploration has always expanded outward from continents to oceans, from Earth's surface to orbit, from orbit to the moon, from the moon to robotic emissaries across the solar system. Interstellar objects represent the next natural horizon. They are practice targets for species preparing consciously or unconsciously for the stars. 3ATLS also reshapes theoretical astrophysics. By analyzing inbound velocity vectors, astronomers may infer correlations with galactic rotation. Objects entering from particular regions of the sky could hint at dense stellar neighborhoods or dynamic scattering zones. Over decades, a catalog of such objects may allow mapping of galactic debris flows. Chemical diversity among interstellar visitors may reveal patterns tied to stellar populations. Objects originating from metal-rich regions of the galaxy might differ compositionally from those formed in older, metal-poor environments. Such comparisons would extend exoplanet science into the realm of physical sampling, albeit opportunistic. Even more profound is the long-term question of biological implications. If planetary systems exchange material naturally, then organic chemistry, and perhaps even microbial life under rare circumstances, could traverse interstellar distances embedded within protective rock. While definitive proof remains elusive, the mechanism for exchange is now observable. 3ATLS stands as a demonstration of that mechanism. On a timescale of millions of years, fragments from Earth itself may wander through the galaxy. Impacts capable of ejecting crustal material at escape velocity have occurred in planetary history. Some of that material could travel interstellar distances. Thus, the exchange is bidirectional. The Milky Way may contain microscopic traces of countless worlds. From a strategic standpoint, the continued study of interstellar objects enhances planetary defense understanding. Although 3ATLS poses no threat, its high velocity illustrates the importance of detection capability. Early identification is essential not only for scientific opportunity, but also for risk assessment. Interstellar objects may be rare threats, yet awareness ensures preparedness. Culturally, the presence of 3ATLS inspires imagination. It invites reflection on cosmic unity. The atoms comprising its structure were forged in stellar furnaces, scattered through a protoplanetary disk, assembled into solid form, and ejected into deep space. Those same physical laws govern matter on Earth. The difference is origin, not essence. When 3ATLS departs the solar system, it will re-enter the vast darkness between stars. Its temperature will plummet, Solar radiation will fade. It will continue wandering for perhaps millions or billions of years before encountering another gravitational domain. Its path is a thread woven through galactic time, yet the encounter leaves an imprint not on the object alone, but on knowledge. Data collected during its passage will persist indefinitely. Archives will store spectra, orbital parameters, rotational light curves. Future scientists may reanalyze those datasets with more advanced theoretical frameworks. The object will be gone, but its informational residue will endure. This is the essence of scientific progress, transient events yielding permanent understanding. The dawn of interstellar consciousness is subtle. It begins not with starships, but with recognition. Recognition that the galaxy is permeable. Recognition that material crosses stellar boundaries naturally. Recognition that humanity possesses the tools to detect, analyze, and eventually intercept such material. 380 Oz symbolizes that threshold. It is a physical reminder that the separation between star systems is vast but not absolute. Gravity, time, and motion bridge the gap. In centuries to come, when interstellar probes depart intentionally for nearby stars, historians may look back on these early detections as foundational milestones. The first visitors, ʻOumuamua, 2 Borisov, 3 Iketilas, will be remembered as catalysts that transform curiosity into capability. The galaxy is not static. It is a dynamic arena of exchange, motion, and evolution. 3 Iketilas is one participant in that grand choreography. Its journey continues outward. Humanity's journey continues forward. And in that parallel motion lies the future of space exploration, no longer confined to the solar system, but aligned with the broader architecture of the Milky Way itself.